We'll be starting up here in about probably a minute or so.
Okay.
Willie, do you have a PDH slide or not?
I don't believe I have a PDH slide.
I'll take that as a no.
I don't believe so. Yeah. Assume no.
Okay. You ready to go, Willie?
Let's do it.
Okay, here we go. Okay, good morning. And hopefully my sound's working. It's being persnickety today. Um, my name's David Orr. I'm the director here with the local roads program. I'm working from home today. Got the plumber coming by, which is just the way things are. Some days that goes. Today we're going to be doing one of our last few webinars. We're going to be doing talking about the basics for bridges and introduction to them. Willy Grimmke, who was with how long were you with Washington County, Willie?
13 years.
13 years. We'll be talking about that. He's got a lot of bridge experience and actually does the NHI inspection class, right?
Bridge maintenance.
Bridge maintenance class.
At bridge maintenance and bridge construction. So
Okay. They all blur after a
they're
while.
all they all run together.
What bridge is that behind you, by the way?
Um, I'm not sure.
Oh, we'll have to investigate that.
I'll have to
Okay.
investigate that.
Well, we'll let you get started. I think we've got some polls. Going to do them inside of Zoom. So we'll do some polls to see who's here. So Jody and Amanda will do that, and then we'll get you started. This is
Great.
worth one PDH, by the way, for those who are online.
Okay, good morning and welcome. We are talking about bridge basics, introduction for bridge owners. I'm Willy Grimmke. I will be doing the uh, webinar today. So our learning outcomes today are to describe what constitutes a bridge, list the components of the bridge, discuss how a bridge carries loads, describe common materials used in bridges, and probably the most important for the folks that are bridge owners is be able to list things to look for as a bridge owner in your bridges. So we're going to start out with some poll questions just to get a sense of who's who. What's your primary job function? Are you public works staff, public works management, an engineer, or other?
Give everyone a few more seconds to answer, but overwhelmingly, it looks like we have a lot of engineers on today.
Okay. It looks like it's time to build up the PDH inventory. Okay. Next question, or next slide, next question. Who do you work for? Do you work for a village, town, county, city, state, or are you in the private sector?
And if you're other, you can throw it in the Q&A. Or you work for the weekend.
Now there's a thought.
So it looks like we have a good mix today.
Oh, good. So we have some village folks, which are near and dear to my heart. I'm on the village board here in Greenwich. Town folks, county, again, my background with county, and then we got some city folks, some state folks, and private sector. Fantastic. Okay. So, what experience? How long have you worked with bridges? Less than a year? 1 to 5, 5 to 10, 10 to 20, or you're an experienced veteran.
Ooh, again, we got a good mix of people. You guys, a few more seconds. All right.
Okay. For you veterans, this is probably not going to be anything particularly new. It's pretty basic refresher stuff. And for those of you that have not spent a lot of time, it may provide some new information for you, or just reinforce some things that you suspected. Okay. And if you are a bridge owner, how many are in your system? 0. Small municipality with 1 to 10, 10 to 25, 25 to 100, or if your state or several of the counties, you have over 100, or who knows? I don't know how many bridges I have.
There we go.
Okay, so we've got some heavy hitters in the over 100, and then we've got some folks with smaller inventory. And I will opine that if your agency has quite a few bridges, you often have the internal expertise to manage and maintain them. And if you have like less than 10, you're often at a distinct disadvantage because you don't spend a lot of time dealing with bridges until they become a problem, and then you're trying to figure out what to do. Okay, so this is a photo of the Ogdensburg Prescott International Bridge over the St. Lawrence River. It's owned by the Ogdensburg Bridge and Port Authority. And what's a bridge? So that's the question of the day. And the answer is, well, it depends. The federal definition is basically anything carrying traffic that has a span of more than 20 feet. So, and under the federal definition, those bridges need to get inspected every couple of years and has an independent bridge identification number. So that's what the feds say. Now, the state of New York and the highway law says basically the same thing, more than 20 feet. But just because it's written in the law doesn't mean the courts necessarily agree. So Chestnut Ridge versus Thomas Howard, and also referring to Brennan versus State of New York, the courts decided to go with the dictionary definition of what a bridge is, and regarding the statutory language, and say if it looks and acts like a bridge, meaning it's span over abutments, regardless of the length, it's a bridge. So it depends on the context of what a bridge is. So essentially, the courts have a fancy legal way of saying if it walks like a duck, talks like a duck, it's a duck. So is this a bridge? And if anybody wants to, raise their hand, chat, whatever, and say yes or no, they're welcome to. I would say, looking at that, the span between the towers is well more than 20 feet, and between all of the piers on the approaches, each of those is well more than 20 feet. So it would definitely be a bridge. This is a little more interesting. So would this be a bridge? and it kind of depends on what the definition is. We have 3 pipes. If the distance from the far limit of the pipe on the left to the far limit of the pipe on the right is more than 20 feet, it would qualify as a bridge by the state and federal legal definitions. But by the court definition, even if it was more than 20 feet, it would still be a culvert. So, is this a bridge? And again, I'll put this in the general category of it depends, and it depends on the definition you're using. By the court definition, it's definitely a bridge because it's got beams that are supported by abutments. It walks like a duck, as it were. But if the span is less than 20 feet, by the New York State definition and the federal definition, it wouldn't be a bridge, but it would be defined as a culvert because it's less than 20-foot span. So again, why does this matter, whether it's a bridge or not? Well, coming back to that 20-foot definition, anything more than 20 feet is on the National Bridge Inventory. It has a unique identification number, and if you look at the center of the photo, there's a green sign with 3306230, and that is the New York State bridge identification number for this particular bridge. Every bridge in the country with a bridge identification number is inspected biannually. Here in New York, the state inspects them, or with either their forces or forces they contract with. In other states, it's sometimes left to the responsibility of the owner. Here in New York, inspection reports are forwarded to the owner on a regular basis. And here in New York, if there are problematic findings, they may result in a flag issuance. It could be a safety flag, meaning there's a safety issue that needs to be addressed. It could be a red flag, which in conjunction with the safety flags often have a 24-hour or 30-day response time, depending on the severity. Or it may be a yellow flag, which basically triggers annual inspections and is something that the bridge owner will just need to keep an eye on, or maybe put on their maintenance program for repair.
Willie, we do have a quick question.
Sure.
What about rail over and under bridges?
Railroad bridges.
No, it's
what?
rail over and under bridges.
Rail over and under bridge. I don't really understand the question.
I think he's talking about bridges that go over rail or under rail. So it doesn't matter whether it goes over water or not.
It does not matter whether it goes over water or not. If it goes over anything, if it goes over a road, if it goes over a railroad, if it goes over just a ravine with nothing in it, or a parking lot, it's still a bridge. If that's the question. The only issue with bridges over railroads is the ownership can be a little bit muddy. I've encountered some where the railroad nominally owns the superstructure and the substructure, but the municipality owns the deck. And there has been a tendency in the past for bridges over railroads to become, quote, orphaned, where nobody wants to claim ownership. So if that didn't clear up the question, resubmit it and re-clarify, and I will weigh in as best I can. Okay, bridges versus culverts. So the statutory definition is over a 20-foot span, but structurally and hydraulically, bridges and culverts are different. With a bridge, as you can see in this photo, we've got abutments, we have a superstructure and a deck, and bridges are typically designed so that the superstructure is not submerged during high water events. There's meant to be freeboard under the superstructure. Culverts, on the other hand, are statutorily less than 20 feet, and in practice, and what we refer to as culverts or large culverts for inspection and maintenance purposes here in New York, are 5 to 20-foot range, the under 5 being pipes. But structurally, they behave differently as they are buried, and a lot of the load carrying capacity on culverts is by the surrounding soil. And from a hydraulic standpoint, they are often submerged partially or totally during high water events. And here we have twin culverts in the photo. Now, these, if their span is long enough, may be bridges, but they behave structurally and hydraulically as culverts. So we'll talk a little bit about bridge components here. And these are the components that are rated on the federal inspection reports, National Bridge Inventory reports. We have the deck, superstructure, substructure, and then we'll also talk a little bit about foundation. This bridge in the photo is Route 2 over the Hudson River between Watervliet and Troy. It's a multi-girder bridge. And we'll start out with deck. So the deck is designed to carry our traffic loads. What the tires ride on. You know, cars, trucks. We also have pedestrians, cyclists in some parts of the state. We also have equine traffic. If you have a lot of Amish or you have, horses. It's meant to provide a nice, smooth, safe surface and act as a cover for the other structural elements most, and I'll say that with an asterisk, mostly. There are still quite a few open grid steel decks that do not act as a cover. Decks are most often constructed of concrete, although there are a number of metal decks and metal variations of metal decks throughout the state. There are also quite a few bridges throughout the state that have timber decks. Then we get into superstructure components, and these are the load carrying elements of the bridge. This is what transmits the load from the deck to the substructure. And it may be as simple as a reinforced concrete slab that has the span that spans the opening. It may be beams or girders, which tend to be the most common. What we see the most of are multi-girder bridges. For longer spans, we sometimes have trusses. And for other much longer spans, we'll have cables superstructure. This photo is sunrise at the Tappan Zee Bridge. This is a cable stayed bridge where the towers and the cables are the superstructure components supporting floor beams below, which in turn support the deck. Substructure components. So these are the elements that support the superstructure and transmit the loads from those superstructure elements. In this case, in this photo, it's plate girders, and transmit the loads from the plate girders down to the foundation elements. Very often and most commonly, substructures are constructed of concrete. Very often they're in compression, and concrete does a really good job transmitting compressive loads. Sometimes they will be steel. And the two primary substructure elements that we see are abutments at either end of our bridge and piers providing intermediate support if that's necessary, if it's more than a single span bridge. And then we get down underneath to our foundations. And our foundations basically transmit the load from our substructure elements to sound bearing strata in the soil. In this photo, this is construction of a bridge foundation, which is on driven H piles. And these piles are driven through soft soils and to refusal with either firm soils or rock. We often have something like this where we're adjacent to active streams where we have potential for scour. So the foundation and the substructure won't be undermined in the event of a flood event. The other deep foundation option that's sometimes used, depending on soil condition, are drilled shafts. In areas where there is rock close to the surface, sometimes we will place spread footings on rock where if we're crossing a waterway and there's not a risk of scour or undermining, or if we're crossing something that there's no real water flow, like a highway, we will sometimes have spread footings if the soils beneath are firm enough to support the bridge loads without settlement. Okay, so we're going to go through some bridge terms here. We're going to start out. Here's a section of a bridge. We have the pier. This is intermediate support. We have a column extending it as a part of the pier, extending from the pier cap down to the footing. We have piles underneath, which are supporting the pier and transmitting loads down to firm bearing soil. This is a multi-girder bridge, so we have girders, which are the superstructure elements for this particular bridge. We have the deck, and the span is the distance from the pier to the abutment. And then we have the abutment back here. So here's a longitudinal view, providing more description of what we're seeing. So back here, we have an abutment with a cutaway, and the abutment not only transmits load, but it also acts as a soil retaining wall. We have columns at our pier. We have piles. We have a pile cap on this pier, and this particular pier is a pile bent pier where the piles are just driven into the ground and a cap is formed on top to support the superstructure, as opposed to the other one, which has pile caps at footing elevation level with columns extending above to the pile cap. We have beams and girders. This one is looks like a pre-stressed concrete type of beam. And each of those beams sit on a beam seat on top of either the pile cap or pier cap and the abutment. We have an approach slab. Many bridges have an approach slab, which basically spans from the back wall back to the abutment. And I don't know if a number of local bridges and some states like Maryland don't often have an approach slab. And in the absence of an approach slab, you will know when you get to where the bridge begins, because there is often a little bit of settlement right behind the abutment. Got a roadway. Very often at the base of near an abutment, there will be a berm, which is a flat area near the top of the abutment, which is often used by maintenance or inspection forces to get access to where the bearings are and the top of the abutment. And we often have a barrier wall or rail along our bridges to keep vehicles on the bridges and from going over the side. And again, we talked about span. So from a superstructure standpoint, here's a plate girder under construction. And the components of the plate girder are our top flange, our bottom flange, and then the port piece of steel connecting the top and bottom flange is the web. We have stiffeners periodically, and this particular one, because it's connecting the cross frame or diaphragm or K-brace, depending on what your local terminology is, that's a connection stiffener. And the other one that has nothing connected to it is an intermediate stiffener. And very often there will be stiffeners over top of the bearings, and those would be bearing stiffeners. And then if it's going to be a concrete deck that's acting in composite with the steel girder, we will have shear studs welded to the top flange to connect everything together once the deck is placed. Trusses. So truss terms. In this photo, we have a pony truss, which means that it's not the full height of, means traffic does not pass under the truss or through the truss. It means it comes up part way. But we have the top cord at the top. We have the bottom cord at the bottom. We have diagonals connecting top and bottom cord, as well as verticals. And very importantly, at all these connection points, we have gusset plates. And those are what basically connect all those portions together. So underneath the truss, supporting the load, we will have floor beams, and those extend basically between the gusset plates at the various nodes. We will have sleepers or stringers extending between between floor beams, and then there's often diagonal bracing to help stiffen the truss and help stiffen the bridge and help the two trusses on either side of the bridge act as a unit. So And looking at the end of the truss, this was Rensselaer County reconstructed this, restored this as a pedestrian bridge about 10 years ago. This is a through truss, and the end is referred to as a portal. And there will be bracing at the portal to tie the two trusses together. And up at the top, there will be sway bracing and diagonal bracing that will tie the two trusses together so they will act as a unit, as a single bridge rather than two completely independent trusses.
Willie, I just wanted to chime in really quick. You do have something in the question and answer
Okay.
about railroad bridges.
Yes,
I don't know if you saw that, but it was just
I did
talking,
not.
it was talking about a time in past history for federal government. Um, I didn't know if it was exactly a question that you wanted to answer, or it was just a statement
Okay.
that I wanted to let you know.
Okay, there are time in past history when the federal government required all railroads to create track maps showing when they own, what they own, so that the railroads could set their passenger freight based on land and they own for the railroad. So bridge structures by track map. The bridge was owned by the railroad at the time of the track map inventory, and there would need to be other evidence to prove otherwise. The sale of the railroad to a different railroad meant the new railroad owns the inventory and still existing bridges unless other. Okay. Okay. Yes. So basically there was historical evidence, and probably someone, whoever the weighed in on that is probably someone from DOT that deals with railroad and railroad bridges on a regular basis. And if it's historic and there's evidence on their track maps that the railroad owns the bridge, they own the bridge. There have been things that were built over time that may not have been on those original maps, and that's when we start to get into the orphan bridge issue. So that it's probably about as clear as mud, and like many things, or like the definition of a bridge, it depends, and it depends on the context and what the historical background is and what the evidence is. So, I'm going to talk a little bit about structural performance and how bridge structural elements behave. Basically, they're designed to each component or element is designed to resist one or more forces, and it may be axial tension, it may be axial compression, it may be shear, flexure, torsion, or a combination of any and all of those. So axial tension, it's basically you're pulling on it, stretching on it. It's like stretching on a rubber band, pulling on a rope. Forces that pull along a member and want to pull it apart. Axial compression tends to push it, push the ends and wants to push the ends together. And if we think of something in axial compression in failure, if anybody's ever stood on a soda can and crushed it, that would be axial compression. But very often things don't fail in crushing in axial compression. It's in buckling because they're relatively slender and they tend to bow out to one side or another. Shear. It's when a force results from equal but opposite transverse force, which tends to slide one section of a member past another adjacent section. And here's a shear diagram with horizontal and vertical shear forces. Now, where we tend to see shear is right near bearings, because we have the load of the bridge on the superstructure element pushing down, and we have the support at the bearing essentially pushing up. So that tends to be a high shear area on our bridge. Flexure, which is what our girders and beams are often in. You've got basically it's getting pushed from the side, and you in flexure you get a smiley face type of deformed shape when something is loaded in flexure on a simple span. Bending force is caused by a moment, and it's transverse loading to the element. And interesting thing with flexure is you get both compression and tension forces in different locations in the member. So in this particular case, in the top surface, you'll get a compressive force, and in the bottom surface, you'll get a tensile force. And that's one of the reasons that for multi-girder bridges, we often build them in composite. So we have concrete on that top surface serving as an augmented top flange resisting compression. Torsion, it's a twisting force. And this is when members tend to twist about their axis. We tend to have torsion issues in curved girder bridges, and those tend to want to twist. And some cable supported bridges, we will have potential torsion under wind loads, and those will want to be resisted. So for structural performance, we want to choose our materials to resist whatever forces those members are going to have to support. So, and the shape of members matters. For example, if you go out to a bridge and you look, tension members tend to be relatively slender. If you look in the bottom of the photo, there are a couple of diagonal rods that those will act primarily to resist tension. If you put a compressive load on those, they would buckle. Compression members would tend to have a augmented or enlarged cross section to try and prevent buckling. Shear zones, you're going to get extra reinforcement. On steel, you often have stiffeners. In concrete, in shear zones, you'll have steel stirrups in your concrete. In high moment areas, might have some sort of additional reinforcement. And in torsion zones or superstructure elements that are subject to torsion, you will often have something to help resist it. It may be additional bracing, like more diaphragms, and diaphragms at not perpendicular but at an angle, or you may have a box or trapezoidal shape, which is more likely to resist torsion. So structural performance of girders. This is a multi-span, multi-girder bridge. And this is a continuous span. So over top of that pier, there's a significant negative moment. And that may have been one of the factors that drove having a much deeper girder over that pier to resist that negative moment. at, I mentioned bearings and shear. So here's a steel plate girder at a bearing. And notice there's a stiffener right over top of the bearing, and that's there to help that girder to resist shear at that location. For a truss, it is largely acting like a very deep girder. Notice that on the photo, it's illustrated with the red members of the truss are in compression and the blue in tension. And very similar to how a girder would behave under load, with the top surface in compression and the bottom in tension. And then the diagonals will vary depending on the configuration of the truss and how it's loaded. Cable bridges. Basically, all those cable elements are in tension. The towers are in compression. And then the floor beams are largely acting, as any beam or girder would, spanning between the cables. So bridge materials, we build them out of a variety of things, most commonly steel and concrete. We may use timber for eons, or we've been using masonry. The Romans built aqueducts and bridges of stone masonry, and some of those are still standing today, over 2,000 years later. And each material has its own advantages and disadvantages. Steel, for example, you can do a variety of things with it, a variety of designs. It's versatile. Strength has improved over the past century or so. I liked having steel bridges in my inventory. It was easy to fix, as long as you maintain it. But the downside of steel is that it is susceptible to corrosion, and that is the Achilles heel. So you need to keep your steel bridges clean, keep water away, and maintain your coatings. So good and bad. You can do great things with steel bridges, as you see in the photo, with the arch, with the cantilevered truss. You can efficiently use it and span significant distances, but the downside would be what we see in the photo on the right, where the coatings are failed and corrosion has started to cause section loss in the bridge. Concrete, it can be economical. It can be cast in a, largely whatever shape you want. And even though it's a little bit porous, it doesn't tend to be damaged by water. And it's very good in compression. Unfortunately, it's not that great in tension, so it requires reinforcement. And most commonly, the reinforcement used is steel, which, if water and chlorides get to that steel reinforcement over time, will cause it to rust and then create other issues with spalling. And here are good and bad photos of things that, advantages and disadvantages of concrete. Here on the left, you have segmental precast, which will be post-tension together. Again, variety of shapes. That trapezoidal shape is good for resisting torsion. The segments are good in compression. And then on the right, we have a bridge deck that's been in service for quite some time. And you can see that we're starting to get some cracking, spalling, delamination. And that is probably due in part to years and years and years of chlorides being applied to the deck for snow and ice control, and the top mat of the reinforcing starting to corrode. Timber. Here's one of Washington County's covered bridges, and was used for many years because it's a renewable resource. We have forests here in New York. It's fairly easy. Wood's fairly easy to work with, fabricate compared to steel and concrete. It's pretty lightweight. But the challenge is it is susceptible to decay. If you have moisture, it will cause the wood to rot, which is why back in the 17 and 1800s, they built covered bridges, because the cover is to protect the wood truss. And here are good and bad with timber. The photo on the left is an interchange outside of Rapid City, South Dakota, with treated timber. Again, arch. It's a fairly dry environment, is performing well. And then on the right is a photo of timber that's getting wet on a regular basis and decaying, and you can see all the water stains. So if you own a bridge, you need to remember the self-evident truths of bridge maintenance credo. From the bridge maintenance credo is all concrete cracks, all joints leak, and rust never sleeps. So if you have a steel bridge, things you want to look for are corrosion and section loss, impact damage. Has it been hit? Is it distorting or buckling, not behaving like it's supposed to? Are you missing bolts or broken connections, broken welds? Do you have failed coatings? If it's painted or galvanized or weathering steel, is that protective coating continuing to protect the steel? Quick aside, we had a number of weathering steel bridges in Washington County, and they were not in the environment that was ideal for weathering steel. And what would happen is, rather than the tightly adhering patina developing, we would start to get flaking and accelerated rusting. In the photo, we can see that A, the coating is failing, and B, we're getting corrosion and section loss, and that can be it. This is over top of a pier under a joint, which apparently has been leaking for quite some time. If you have concrete, things you want to look for how it's performing. Do you have spalls, chunks of concrete popping out? Do you have cracking where you're not expecting cracking or shouldn't have cracking? Efflorescence, which indicates that water is migrating through your concrete, and then it's the white film you see at the bottom of that concrete, and that's minerals leaching out of the concrete and then depositing on the surface. Do you have unsound concrete or soft concrete? And you can determine that by banging on it with a hammer or piece of rebar, and it will definitely sound differently. Is your rebar exposed? If it's pre-stressed or post-tension, do you have exposed tensioning strands? And are they corroded or broken? If you have timber, you want to look for splits and cracks, broken or crushed. Some of our covered bridges had bed timbers where the truss sits on the abutment, and some of those would become broken or crushed over time. Is anything moving? Do you have staining and moisture damage like we have in the photo? And if you have accumulated debris, that's going to trap moisture, so you're going to want to get rid of that. At your substructures, is it plumb and sound? Is it like it's supposed to be? Are your back walls tipping or rotating? Are your beams or girders hitting the back wall, or do you have the clearance you need to have? Do you have any spalling underneath your bearings? Are your weep holes working? Like after it rains or after it's been wet a while, do you have a little bit of water staining right at the outlet of the weep hole? If you look at where your wing walls meet your abutment, is that joint pretty uniform top to bottom, or do you have something rotating where one end of the joint is a wide opening and the other is very narrow? On your columns at piers, how does that pier look? Particularly at the mud line, water line, ground line. Is everything plumb? What do those pier caps look like? Do you have, spalling concrete, exposed rebar? Joints. So there are two kinds of joints. There are those that are leaking and those that will. So you want to go take a look at your joints, because basically leaking joints will ultimately lead to some kind of superstructure damage. So you want to look to see if they're leaking. If you've got some staining or you've got evidence of puddles on the abutment or pier cap, look at these seals if they're meant to be sealed joints, to see if those are still in good shape and intact. One of the things I like to do is, looking at joints, is go underneath and look up and see if I can see daylight. If it's meant to be an open joint, like a finger joint, is that water catchment or trough system working like it's supposed to? Or is it full of debris and backed up and overflowing? So you just want to keep an eye out for that. Moving down, bearings. How are your bearings behaving? Are the anchor bolts like they're supposed to be? Is it overextended? Is it corroded? Is it frozen? Does it need to be lubricated? We did several years ago, did a paint job, and we had steel rocker bearings, and sandblasted them and could see daylight underneath the rockers. So that paint job became a bearing replacement project. Okay, so we're nearing the end. So now it's time to do our PDH questions. By the federal definition, a bridge is longer than A, 50 feet, B, 5 feet, C, 30 feet, D, 20 feet, or E, 100. Survey says 96% say over 20 feet. So yes, thank you for paying attention. Next question. What forces tend to twist structural members? A, flexure, B, shear, C, compression, D, torsion, or E, tension?
Give everyone a few more seconds to answer.
Okay. Survey says torsion, and that is what we were indeed looking for. Okay. Okay, what distress is not something to look for in steel? Something we don't care about in steel. Corrosion, distortion, debris, impact damage, or decay.
Like we have some mixed reviews on this one.
Okay.
Give everyone a few more seconds to answer.
So what we were looking for is decay. Debris, I'll start out. Corrosion is something we definitely want to look for with steel, on steel. That's the Achilles heel of steel. Distortion, if it's undersized or not performing correctly, distortion will be an issue. I will point to the I-35 bridge collapse out in Minnesota several years ago. There were gusset plates that were distorting. Debris is something we need to look at on accumulating on steel because accumulated debris will also collect moisture and tend to accelerate corrosion and coating damage. This is particularly an issue on trusses where we have nooks and crannies at the gussets. So we want to make sure our steel is clean and we don't have accumulating debris. Impact damage can happen. What we really don't care about with steel is decay. That's not, steel will corrode. Decay is an issue we're looking for on timber. And what part of the bridge carries the load from the deck to the substructure?
Everyone, a few more seconds here. There we go.
Okay, so we are looking for superstructure. Foundation carries, transmits load from substructure to ground. Deck from the vehicles to the superstructure. Joints, if they transmit load, it's between superstructure elements, and bearings are between the superstructure and the substructure. Okay. Anybody have any questions? If not, I want to thank you all for your attention, and hopefully you got something, or you got out of this, or you got some refresher and just reminded you of things you already knew.
Did we get the question about the pedestrian bridges answered, Willie?
I did. Oh, pedestrian.
Does it include pedestrian bridges?
Pedestrian bridges do not necessarily have a bin, although some may.
I think the rule is if it crosses a public right of way.
But if it public road or
Yeah.
I
Yep.
just did an inspection on an old rail bridge that became a pedestrian trail. That one did not have it was not on the National Bridge Inventory because it didn't cross a public road.
Right.
It looks like that's it. Thank
Okay.
you. If you guys have any other questions, you can shoot us an email at clrp@cornell.edu and we'll get it over to Willie or David and get you the answer. Oh, got one last one.
One last one. Okay. What's a good repair procedure and product for concrete deck that is spalling? Depends on the extent of the damage, but what you'll want to do is remove the unsound concrete. Um, make any repairs to the rebar that could be causing it. Sandblast and clean. If you use a cementitious material, you'll want to make sure your saturated surface dry. And depends, and if you use other materials, follow the directions, basically. Very often it's standard concrete or mixed concrete.
The big
for
thing I'd say
spalling.
there is figure out why it's spalling. Makes
Yeah,
it
and
then
it's
come back.
right. And it's very often that you've got chlorides, you've got cracking or concrete that chlorides have penetrated through to cause the rebar to rust, which expands and causes the delamination and spalling.
Yep. So it may be a case of looking for sacrificial bars or figuring out a long-term sealing process or even something
Right.
more expensive. Yeah.
And or maybe using sacrificial anodes on the existing bar after you've cleaned the rust off.
Enjoy the rest of your Tuesday.
Okay, thank you.
Thank you.